Yes, sir.
And the screen is also visible, right? Okay.
Yes.
Okay. So last time we were discussing alternating currents. We did this root mean square of voltage and current, and then we discussed the power loss in alternating currents. Let's finish this topic of power loss in alternating current. We'll also discuss the uh, average power loss and the maximum power loss from moving from this equation. Is there any questions so far from anything that we did on this topic of alternating currents?
No, sir.
No questions. Okay. So this is what we wrote down for power loss. We know that the power loss is also going to be a sinusoidal kind of function. It would be changing because the current is itself continuously changing, and the power is related to the current and voltage by I times V, right? And then from Ohm's law, we know that V is equal to IR, so we substitute and get P equals I squared R, from where, if you remember, the current for a sinusoidal or an alternating current expression is given by this equation, where I naught is the maximum current and sine omega t. So if I square this thing, I get I naught square sine square omega t, and then this R. So we write it like this. Okay, so we have this so far. We can talk about the maximum power from this expression as well, right? So first, let's look at the graph for sine square omega t, right? So if I have this, let me, how do I do it? Let me just draw the graph over here for sine squared omega t. Okay, so this is t, and this is my y-axis where I'll plot the sine graph. Sine squared graph is going to be like this, and then again like this. It will not go down because it's a squared graph, so it will not take any negative values. So it's something like this, right? And this is the maximum value that I can have on the y-axis, and this is the minimum value, which is 0. So the minimum value for a sine squared omega t is 0. Okay, what about its average value? What is, suppose, let's call this thing, if this is v, or you can say that this is I, for example, I or V, right? It's a sinusoidal function. Then this will be I naught. What will be the average value of this graph? Before you tell me that, can you tell me what would be the average value of a simple sine graph? What if I want the average of this thing?
Average will be 0.
Average will be 0 because we have this part that is upstairs positive, and then you have this part which is exactly the same but negative. So when you average out these two parts, you get 0. This straight line, this axis, you get back this time axis. Now, this, in the same way, if I look at this graph, which is a sine squared omega t graph, what would be its average? Its average value will lie midway between on this line, if I extend it like this, right? So because as you know, average value is taking two values, which is maximum and minimum, and then dividing it by 2. The maximum over here is I naught, minimum is 0. And then these are the two values. So we divide it by 2. So this is I naught by 2, which is the average current, sometimes written like this. Average, this means that it's the average value of the current, which would be I naught by 2 in this example. Actually, this is not current. I should write it as power, right? Because current is not a sine squared function. So I'll just, let's just say that this is some P naught maximum power. This is P naught, and then this is. Okay, so is that clear?
Yes, sir.
Okay, so we can then go a bit further. I'll go to the next page. That this P, what was this thing? The average power, right? Average power is the expression we wrote down was what was it? I keep forgetting. P naught by 2, right? So the average power, which is P naught by 2, is then what is P naught? It is I naught squared R by 2, right? Which is then you can write this as V naught squared by 2R, right? So this is the average value of power that I can get, or the power loss that I'll be getting in an alternating current circuit. I can, from this equation, I can write average value for voltage as potential drop as well. Average potential drop as well. How? Because we know that this is P. This is the same thing as V times I, or it is the same thing as V squared over R, average. Now, on the right side of the equation, I have the RHS right hand side is V naught squared over 2R. So from this, I can write that if you can cancel these R's, then V squared average value is V naught squared by 2 as well, which means that the average value of the potential drop in an alternating current circuit is V naught by under root 2, which is again the same thing as the one we discussed before, the r.m.s root mean square value of potential drop. Okay, any questions so far?
No, sir.
Okay, so the idea of r.m.s voltage is clear as well. The fact that it is the value of the direct current or or the voltage that is coming from that direct current that would convert the energy at exactly the same rate as if it were uh, uh, a direct current circuit, right? Or the voltage is equivalent in direct current terms, this r.m.s value of the alternating voltage. Okay, so let's do a problem. Okay, so suppose that you have mains voltage, and that is rated at 230 volts and 50 hertz. Right? In the UK, the frequency is usually 50 hertz, and we want to calculate the peak voltage. Right? What is the peak voltage that I can get from this thing? Before that, can you tell me what does it mean that the mains voltage is rated at 230 volts and 50 hertz? In terms of the RMS value. This value 230 volts is the RMS voltage, right? This is the root mean squared voltage. So if you want the maximum voltage, it's not 230 volts. The maximum voltage that you receive is V naught time, this value 230 volts times square root of 2, right? Which is slightly higher than this 230 volts. Okay, so is that clear?
So can you explain that one more time?
Yeah. So this voltage, the mains voltage that you get from your supply, even your households, it's rated at, if it's rated at 220 volts, or sometimes or in the UK it's at 230 volts. These values of voltages are your root mean squared values of voltages. They are not in but from the main supply you're getting the actual, the peak voltage that you can get is higher than this voltage, right? And the peak voltage, which was this value V naught, is what we want to compute, right? So V naught, from this equation, V average is equal to V naught by square root 2, says that the peak voltage V naught is the product of square root 2 times the average root mean squared value of voltage. This thing is the RMS value. So you can see that if I multiply this with the square root 2, the voltage that I get is 325 volts. This is the peak voltage. So if I plot this thing like this, actually it will not be looking exactly like this. It will be something okay, this is not an accurate graph, but the peak value of potential drop is this one that we computed, 325 volts. And the RMS value of this graph is the one that we have as the mains voltage, which is 230 volts. It's 325. Yeah, maximum is 325 peak voltage. Okay, so is that clear?
Yes, sir.
Okay. Now, if you want to compute the energy that was dissipated if suppose that let's continue this problem and say that you want to calculate the energy loss when an electric fire of resistance 25 ohms is run from the supply for 1 hour, right? So I have a resistor, and the resistor is of 25 ohms. I want to compute that if I run some AC current through this resistor for t equals 1 hour or 3600 seconds, how much energy will be lost in this resistor. So how can we compute that? The energy that's lost, we'll always be using the root mean squared value of potential drops. So the energy that is lost when you run AC current through this resistor of 25 ohms, you'll get the energy loss as V, which is V r.m.s squared over R times time. How did I get this equation? This equation is just coming from the fact that power is energy per unit time. So energy is power into time. So power for an AC, the average power is given as V average squared over R, and then multiplied by time to get energy. So the root mean squared value of voltage, which is always the mains voltage, is the root mean square value is 230, and then you'll square this, multiply by 3600 divided by 25 ohms. So there is an energy loss of 7.6 into 10 raised to power 6 joules if I run an AC current through a resistor of 25 ohms. So you have to remember that the r.m.s in calculations, r.m.s values is used and not peak values, because the average value is the value that you're likely to get when you're running your alternating current. It is always the average value that you will be using for your calculations. Okay, any questions so far?
Sir, why can't we use the peak value again?
Oh, because when you run your AC current, it's alternating between maximum, minimum, maximum, minimum, maximum, minimum. So the r.m.s value is the value that you would be most likely getting out of your whether it's the current value or it's the potential difference value. It is always the root mean squared value that you would be getting, and not the peak value. The peak value is the maximum value that you can get, but it is the root mean squared value that you are most likely to get when you measure the current.
All right, sir.
Okay. So with that, let's move to the concept of transformers. Wait a second. Okay, the name kind of says what it does. It transforms something, right? Now, let's see what it is. Suppose that if I have to charge my cell phone, right? If I want to charge my cell phone, I plug it into a wire and I plug this into a socket, right? Now, when I plug this into a socket, the main supply, which is usually 230 volts, if this 230 volts enters or hits the phone, it's going to damage it. 230 volts is a very high potential to charge your mobile phone. It can cause a lot of damage to the cell phone, its accessories. They'll burn, they'll explode, or anything. What we need to do is we need to step down the voltage and just provide the cell phone enough voltage that it requires to get it charged safely. right? And that is done with the help of a transformer. The transformer in the charger will transform the voltage that is coming from the supply into a set voltage which is safe to charge your mobile phone and not cause any damage to it. So the transformer, maybe it's a 12 volts is required to safely charge your phone, then the transformer will step down the voltage to 12 volts and then send it through this wire, and that will safely charge your cell phone, right? Now, before you even get the mains supply, which is 230 volts, even coming to this 230 volts had passed from a transformer and stepped down. So initially, we have these power cables, and the electricity alternating current is transmitted through these cables on these towers like this. So if I can draw them. So this is how the electricity is transformed. These are very long cables, and the potential difference that is sent through these cables is of very high value. So the potential difference of these cables is usually about 10, could be about 10 kilovolts, which is 10,000 volts, which is extremely a large value of potential differences. And of course, we don't want any value near that coming into our home, through our home, right? Because it's going to explode, blow everything up. So from here, when the electricity is supplied to your home, it goes through a transformer again, and the transformer steps it down to 230 volts. Now, there are multiple reasons why this large value of potential difference is sent through these cables, because there will the electricity that it has to travel a lot of distance, because your the supply is sent from an electric company, and it has to electrically supply the entire city, or the entire usually the entire city, right? So to power the entire city, you have to have very long cables that are sending those electricity or voltages. And because the cables are so long, there will always be some resistance and a lot of other things which will cause a drop in voltages. So that's why you send a very large amount of potential difference initially, and then you use a transformer to step it down to a safe value, and then you can send it through your home. Okay, is there any questions from this thing so far?
No, sir.
Okay. Just give me a second. Okay. So the question now is, how does this transformer works? What is this box that I'm labeling as T? What is inside it? What is it made up of? How can I step down the voltages, right? What you do is, the transformer is made up of coils. And what you do is, you take a coil. Let me see, how can I draw it? Okay, so this is my coil, right? And it's not just one turn, it has many turns. So it's a coil of wire with some turns over it. Right? Now, you measure the number of turns over here. You say that these number of turns are NP. P, because this is just one coil, we also take another coil, and we'll talk about that. This is known as the primary coil, and the number of turns on the primary coil is NP. So this is the number of turns on primary coil. Then you take, in exactly the same way, another coil, like this coil of wire, and it has some turns on it as well. And this is called as the secondary coil. And the number of turns on secondary coil, which is NS, is the number of turns. Okay, now what happens is, you know that when you supply, you're going to supply some alternating current through these coils. So let me just demonstrate that by this thing. So you're going to supply some AC current. When the alternating current is supplied through a primary coil, it's going to produce a changing magnetic flux into the secondary coil, right? And we know that this changing magnetic flux is going to give rise to an EMF. How do we know that? We know that EMF is minus d phi by dt. So if there is a changing magnetic flux, then there will be an EMF induced in the coil, right? Now, let me write this as when you send AC through the coil, it produces changing magnetic flux. Or an alternating magnetic flux. Now, this alternating magnetic flux in the transformer is then cut by the secondary coil. And that cutting of that alternating or changing magnetic flux is then what is producing this EMF minus d phi by dt, which means that I can write down the EMF for the primary coil and the secondary coil as, so V for P, the potential or the EMF induced in the primary coil is going to be minus the absolute value of the potential drop will be d phi by dt times the number of turns NP, right? So if you remember, this is then just NP d phi by dt, and this will give you the EMF that is induced in the primary coil. In exactly the same way, you can write down an equation for an induced EMF in the secondary coil as this thing. So it is NS d phi by dt. Now, from this, both of these things are equal, have a d phi by dt, which means that I can say that Vs over Ns, which is d phi by dt, and over here, the second one is Vp over Np is also d phi by dt, which means that these ratios then Vs over Ns should be equal to Vp over Np. And we can rewrite this equation as Vs, take that Vp over here, so it will divide, and bring this Ns over there, so Ns by Np. Right? And then usually you can then just also flip this to say Vp over Vs is equal to Np over Ns. And this is the equation of a transformer. Using this equation, okay, now you can use this equation to see the amount of turns that you need on your coil to get a desired voltage or the EMF induced in that coil, right? So this, what does this tell you? This equation tells you that you can adjust the number of turns on the coil. Simply adjusting the number of turns on the coil is going to give you different values of the potential drop or the EMF induced, not the potential drop, but the EMF induced in the coil. So Vs in this is the EMF that is induced across secondary coil. Vp is the voltage across the primary coil, right? So the voltage across primary coil is coming from what? When I send an alternating current through the primary coil, that causes a changing magnetic flux in the secondary coil, which then induces EMF in the secondary coil, right? And Ns is the number of turns on the secondary coil, while Np is the number of turns on the primary coil, right? So, which means that this equation is also telling you that for a step up, now there are two types of transformers, right? There is a step up and there is a step down. The name again says it all. Step up has to increase the voltage, and then, so initially you can have a less voltage, finally you will have a higher voltage. So for a step up transformer, NP is less than NS, or NS is greater than NP. For higher number of turns, I'll get a higher voltage. So I make the secondary coil with more number of turns. So the EMF induced in the secondary coil will be very high compared to the primary coil. For a step down, it is exactly the opposite. Now you want to step down the potential or the EMF induced. And you can do that by keeping NP greater than NS. So NS is now less. The number of turns in the secondary coil are less, which means that the voltage that you would be getting in the secondary coil, the EMF induced in the secondary coil will also be less. Right.